Uh, can you please confirm if my screen is audible? If my screen is visible, please?
Yes, sir, we can see. Yes.
Thank you very much. Thank you. I hope I'm audible. So, hello and welcome all to this last CPD webinar on box culvert design to Eurocodes using MIDAS Civil Annex. My name is Sumant Kushwaha, application engineer with MIDAS IT, and I'll be taking you through this webinar for today. Before we begin, I would again like to express my gratitude to IC Sri Lanka for giving us this opportunity to share our knowledge and showcase MIDAS Civil Annex capabilities to engineers in Sri Lanka. My presentation today is focused more towards students and practicing engineers in early careers. Although I do hope that everyone gets to learn something new today. So for this session, I have two main motives. First, to showcase MIDAS Civil Annex capabilities to help engineers in this design of 3D box culverts. Secondly, to discuss about some of the practical aspects of box culvert design and provisions of Eurocodes. This is going to be the agenda of today's presentation. First, we'll have a look about the introduction to box culverts or culverts in general. Secondly, we'll focus on modeling of culverts, how easily can we model the culverts in MIDAS Civil Annex. Third, we'll discuss about loadings as to what are the loads applied in box culvert design, and we'll also look at the moving loads and some other aspects that we again will not be considering in today's modeling part, but still it's good to know. Fourth are the ones, the other design considerations that are the ones that we'll not be covering today, but good to know for engineers during the practical aspects or during the practice. Fifth is the aspects of soil structure interaction. We'll be discussing what all things we need to capture while doing the design of box culverts and how often we do ignore the effects of soil. Sixth, construction sequence and why it matters in box culverts. Seventh is we look at the detailing and durability and local practice. Okay, so let's begin the presentation. This is a speaker's profile. I have technical. I'm application engineer at MIDAS IT with consultancy experience in MNCs on buildings and infrastructure projects. I have worked with companies such as Rambol, Miyamoto, and L&T Constructions. I hold a master's degree in structural engineering from IIT Guwahati. So one disclaimer, the information, opinions and engineering views presented during this webinar are solely those of the presenter. They are shared for educational and professional discussion purposes only based on the presenter's understanding and experience. Those views should not be interpreted as official positions or endorsements of IC Sri Lanka or MIDAS. Participants are encouraged to exercise their own professional judgment and refer to the applicable codes and standards while making engineering decisions. So now we'll cover through the first module of this presentation, which is Introduction to the Box Culverts. So what is a culvert? A culvert is basically a structure that provides a passage for a watercourse, drainage flow, or similar service beneath an obstruction such as a road or railway. Though the definition is not very clear, Syria 689 gives a useful distinction. A culvert can be described as a closed conduit carrying a watercourse beneath an obstruction, whereas a bridge carries a road or railway over the watercourse. As you can see from the pictures, these are the box culverts that allow the drains to flow beneath them. The main purpose is to control the flow of the stream and the pedestrians to skip the traffic. Sometimes you can have the uh, loadings on the upper as well as the lower level of box culverts. It is not always the case that you'll have just the pedestrians. You might have a moving load traffic over these lower levels as well. What are the different types of culverts? The type of culvert is based on number of factors, including hydraulic, upstream elevation, and roadway height and other conditions. The different types of box culverts are pipe culvert. Let me take this pointer, please. Okay. So this is a pipe culvert. Then we have a pipe arch culvert. Obviously, because of the hydraulic requirements, you would want to have a bottom portion with a larger width. And then you'll have a box culvert, which is this one, bridge culvert, metal box culvert. Configuration choices that shape the whole design. Whether you are going to have a single cell or a multi-cell depends on the width of the stream, first of all. So multi-cell introduces differential settlement between the cells and interaction at the shared internal wall as well. But mainly it depends on the width of the stream that you have to cover for. Cast in situ versus precast. Precast units have a different creep shrinkage history at the time of loading than cast in situ. Joint detailing between the units become critical. Portal versus closed frame. Open base portals rely on bearing capacity directly under the walls. So you have to provide foundations for these or the wall foundations for these open base portal frames. Whereas closed boxes redistribute load across the full base width via the slab or the base slab. Skewed crossing versus orthogonal. So generally, if you have a orthogonal crossing, that's much better orientation to get your culvert and the road aligned with. However, that is not always the case. So sometimes you might have to design for the skewed geometries of these culverts. Please note that orthogonal is quite simpler, but when it comes to skewed crossings, factors such as torsion design and the additional forces in the corners also come into play. What are the advantages of box culvert? It is a rigid frame structure and easy to construct. It is suitable for non-perennial streams and when the soil is weak. The The pressure on the soil is reduced due to bottom slab, so lesser thickness requirement. It is very economical due to their rigidity and no separate foundation is required. If it's a precast, the erection is very easy. If it's cast in situ, still compared to the other foundations, the box culvert offers you a major advantage. It requires minimum maintenance and prolonged service life and offers you the reusability. For example, if you can lift the cast in situ culvert, if you have casted with the hooks arranged, so you can of course move it to a different place when it's no longer required on the same route. What are box culvert components? So the box culvert has different components. On the bottom is the longitudinal section of the box culvert, and here we have the section cut of the same box culvert. So as you can see, this particular level at the bottom of the slab, this is the top of the bottom slab or a base slab is called the invert level. These are the hydraulic design requirements, which is defined by the hydraulic team. Then you have a roof slab, which is the top slab or the deck slab over which the traffic moves. Then you'll have a side walls. The internal wall, because this is a single cell box culvert, that is why you see we have two outer walls. Whereas if you see the diagram below, you have double cell box culvert. So the internal wall will be, the middle wall will be an internal wall. The base slab is this one or the invert. Head wall, wing walls are these ones. Head walls, sometimes you extend the height of the end walls above over which you support the balustrade. So it becomes basically a head wall. Wing walls are these ones, apron or cutoff wall. So the extension of these wing walls, we provide the aprons. These are required for the hydraulic design. Apron slabs are provided upstream and downstream to control the flow at inlets and outlets. That is, a stable transition between culvert and watercourse is provided by these apron slabs. One of the important hydraulic design considerations. Now, cutoff may be provided to prevent scour from progressing beneath the apron, reducing seepage paths, preventing undermining, providing additional hydraulic protection. This in turn increases the service life of culverts. The approach fill is the soil forming the road embankment above and around the culvert. So this is the soil here would be the approach fill. Okay. I hope the users or the viewers are clear of the box culvert components. When going on to the modeling part, we'll be looking at some of these components again. The Eurocode suite governing a box culvert design. EN 1990 basis of structural design will give you the limit states of load cases that we have to consider along with the load combinations, partial factors, along with the design working life. EN 1991 part 1 of 1, which is EC1, actions, densities, self-weights and imposed loads. EN1 part 2 governs the traffic loads on bridges, which will give you the moving load models of LM1 and LM2 that will look into this particular presentation in the next slides. Then EN 1991 part 1 of 5 gives the thermal actions. EC2 or EN 1992 1 of 1 to 3 gives the design of concrete structures. Basically, EC2 is basic governing your concrete design code. And EC7 is your geotechnical data, which will give you the bearing resistance, earth pressure settlement, and spring stiffnesses. Okay. Now, the limit state philosophy or the design basis, we'll have different limits to check. The ULS limits or the ultimate limit state, which will cover the structural strength, the sliding or bearing of foundation, uplift or flotation of the whole box. The SLS or the serviceability limit states will cover your crack width control, which is a durability consideration, and which is also important because these are buried structures with water facing concrete. Deflection rarely governs these stocky box sections, but still are the SLS checks. Design working life of box culverts is defined in EN 1990 and is defined as 100 years design working life category, similar to bridges. This affects the durability and partial factor choices. Partial factors are combinations dependent. We have gamma G, gamma G for permanent loading, gamma Q for variable loading, and different psi factors which differ between persistent, transient, and accidental design situations. Construction stage is also a distinct design situation. Generally, when we would design, we would not consider for construction stages, but we should be aware of the construction stage analyses when we are designing for our box culverts. Moving on to the modeling of culverts. Now, I'll try to demonstrate using MIDAS Civil Annex how easily can we model the box culvert. But first, we need to make up the decision why we need a 2D frame strip or a 3D shell model. So in general, today we are going to look at a 3D box culvert design. However, mostly people, when the box culvert is long enough and it's symmetrical in nature, people go with 2D frame analysis using unit width strip. 2D frame analysis is valid for long, straight, uniformly loaded, non-skewed culverts with reasonably uniform support. Fast, transparent, easy to hand check, and good default starting point to get the idea of how much reinforcement should be there and what would be the forces in your sections. However, this 2D frame assumption cannot capture transverse load spreading, skew effects, or width-wise differential settlement if you have any. So if you don't have these things, or if you have the other things such as skewness, or say you want to capture the transverse load spreading or widthwise differential settlement, or the soil or geotechnical strata demands that you have, or you capture the differential settlement or the difference in stiffnesses of the soil, we go with a 3D shell or plate model. These would be helpful for skewed crossings with multi-cell culverts with variable subgrade, where concentrated axle needs realistic 2D spreading. So load spreading will look into a bit about load spreading in our later slides. Captures transverse distribution and torsional effects that a frame strip cannot. More setup effort, of course, and result need equally careful interpretation of plate results, or even a higher effort would go into interpretation of plate results. Now in MIDAS Civil Annex, we have different wizards box that can help you easily generate the geometry and some of the most common loadings in the box culvert. Not just the box culvert, you can also generate other geometries of culvert. First would be the box culvert, the default closed frame configuration for orthogonal crossings, of course. Second is box culvert 2D model as well. So in MIDAS, we also have a 2D box culvert design as well, which will again use the unit width frame strip idealization. If you have skewed culverts, we also allow to model the culverts with skew or even culvert with radiuses. Frame with wing walls. The wing walls can also be modeled in all these options: arch box culvert and arched culvert. These are the different culvert designs or the models that geometries that can easily be generated using MIDAS Civil Annex. Let me demonstrate you because I would want the users to have the feel of the software. I'll just demonstrate to you how we can generate the different geometries here or create the different geometries here. Since the viewers are already familiar with MIDAS Gen NX, most of the features that we'll be covering in MIDAS Civil can be performed in MIDAS Gen NX as well. However, the moving load codes, which are mostly bridges specific, will not be there. So that's a bit of manual work that will go at the user's end. But in case you have other aspects of bridge designs, then MIDAS Civil NX could be a useful or a very useful tool for you. The interface is almost similar to MIDAS Gen NX. On the top, we'll have the main menu. Then we'll have the menus arranged in the same sequence as we had in Gen. We have two tree menus, one on the left and one on the right. In the bottom, we have a dimensions or the dynamic dimensions, and we have a slider button. So now, without a further ado, let's move to the modeling part. I'll try to demonstrate some of the models that can easily be generated using the wizards. Okay, so just sorry. Okay, so we have set the units which are currently in kilonewton meters. So we'll input the parameters mostly in meters. So now we have different wizards, of course. We have slab RC slab bridge design, RC box wizard, PSC box wizard, which can be used generated by pre-cantilever method, MSSS bridge, FSM method, ILM method. We have pre-stressed composite bridge wizard, steel composite bridge wizard, and steel girder options. We also have tools for suspension bridge designs or cable stayed bridge designs. RSI analysis also available in MIDAS Civil NX. So we'll look into 3D box culvert modeling. So for example, let's first of all create the 2D model. So I'll click on this 2D model. The purpose of this is to show to users how easily can we create the model in MIDAS Civil NX. I'll just select some grade. I'll add the material. I hope the users are now familiar with the design, of course. So we'll add the spans. This is a normal type frame. We are now generating the two-dimensional line model for now. Okay, we have the grade here. We have spans defined. Then we'll use the default dimensions here, and then let's hit apply. So this is the low model that is created, and we'll have the basic loadings of dead, self weight, and then we'll have thermal temperature. I forgot to show you what all the options were there. Okay, so we defined the span as to how the geometry would look like along the direction of the road. Then we have the carriageway width definitions in here in the wizard. Then we have the loadings, the static loading part, which can easily be generated directly by the wizard based on the simple input parameters. So this is what has been defined. Now let me show you how we can model. We'll model some 3D options as well. So normal type frames without any base slabs. I'll keep 5 meters still and no wing walls, and I'll change the units. I'll just switch off the loads. Now you have most of the things that you would want in your model to start with. So the supports have been modeled. The roof slabs have been modeled with plate elements. If you can go to workspace menu, here you'll be able to see all elements have been defined with plates. We did define the mesh size of plate element as 0.5 meters. If you want to have a higher plate size or a lower plate size, you can control for that as well. Then we have support types defined, which is fixed in all the 6 degree of freedoms. Then we have different loadings part as well. Okay, so let's now see how we can generate the pi frames as well. So pi frames are also one type of culverts. So 3D pi type. I'll change the dimensions bit. Size of element to be 0.5. This is the angle of the pi frame. I'll keep it as 75 degrees, and let's change the height to 6 meters. In the transverse direction, here we'll input the values of P. This is the number of bearings, and then let's assign them. This is how the complicated shapes which would require a lot of manual effort can easily be modeled in the software. Okay, so what we'll do now is I'll try to generate the model now for a 3D box culvert. So we looked at, just a minute, probably I should have shown you other options as well. Okay. So let's see how we can model now box culvert, because today's topic is on box culvert. But before that, I would like to discuss about what are the different inputs that go in the model. Currently, I just inputted the values to demonstrate how easily we can create the model. But there are different inputs that are required to be able to create the model, of course. Right. So we'll have geotechnical inputs. So let me just move back to the presentation. So we'll have geotechnical inputs that come into the structural model. What would be those geotechnical inputs? Of course, we would require a bearing resistance of the soil. Generally, as a structural engineer in a structural model, we do not exactly model the bearing capacity of the soil. We model it as a springs, which will have a subgrade stiffness. The input of subgrade stiffness is generally provided by geotechnical team. However, there are standard textbooks which can derive the subgrade stiffnesses for you using empirical methods. Bowles' book is quite well known in the industry for such estimates of soil subgrade modulus based on simple SPT values and plate load tests. Groundwater level and seasonal variation are the inputs required by the hydrology team to determine the levels at which your invert level as well as the bottom or the soffit level of the top slab will be determined. There are consolidation or settlement parameters that have to go in the model if there are any to be able to study, because the purpose of modeling a 3D was one of the factors of settlement as well. Fill and backfill material properties are the geotechnical inputs. So you need to know the unit weight of the soil, the friction angle of the soil, and the compaction specifications, such that the soil properties that you have assumed or that exist on the site are not changed by the mechanical compaction later on, which would again increase the lateral forces on your box culvert. These soil properties will be required for the determination of earth pressure coefficients. Also, we need to know the corrosivity or the chemical aggressivity of these soils. This will help us determine the clear cover of the clear reinforcements, determine the grade of concrete that we have to use. The durability requirements are mostly governed by the environment, of course. So it affects your grade of concrete. Sorry about that. Okay. So it affects your grade of concrete, your cover to reinforcement, as well as your crack width limits. So now we'll move to loading as per Eurocodes. But before that, let me complete the geometry or generate the geometry so that we can discuss about the loadings as per Eurocodes in the box culvert design. Okay. So this is a new model, and last I'll just delete this metal property as well. So same as we'll be using the wizard, but this time I'll be generating a box culvert with wing wall dimensions. Okay, so RC box frame design. We have box culvert. We want to generate a three-dimensional box culvert. We'll define the grade of concrete again. So press these three dots and you'll be able to define the concrete grade. See 35, 45, and rest of the parameters are not required for the inputs. Okay. Now here you also have the option to save the wizard. Whatever inputs you inputted in this particular frame, you had the option of saving those parameters as well. So next time, whenever you want to use it, or say you want to change one or two few parameters, you can just go back, open this, click on this wizard file and open. So the properties will by itself update whatever the inputs were required for plate elements would be updated. I'll just change the plate size or the mesh size that I'll be using for this particular design. Now for box culvert design, what are the different inputs, right? So you can create both three-dimensional or 3D box culvert. If you click on 2D box culvert, some inputs would not work now because of course those work for a 3D box culvert only. Okay, so these are the inputs. I'll try to show you what are the different options that we have here as well. Okay, now material grade, if you have two spans, so I want to model a two cell box culvert, so that is why I'm modeling two spans of 5 meters spacing. Size of plate element is defined by zero point 0.5 meters. Wing wall, I'm trying to model a wing wall as well, which will have a thickness same as that of a wall. So I am keeping the top slab thickness of 0.45. For the sake of demonstration, I am keeping most of the thicknesses limited to 0.45 mm as well. But I'd suggest engineers to go for optimized sections, of course. But when we go for optimization, we'll have to look about other aspects of the design as well, which we generally tend not to cover in our main design part. There are aspects of construction staging, there are aspects of site requirements, site compaction, and many other factors are there, right? So these optimizing to a level where any bit of accidents can make your structure fail is not a good idea, and the cost that goes around the revision is higher. So the better way would be to design the structure with some margin of safety so that anything minor happening on site can easily get absorbed in your designs and you don't have to update the design every time. Okay, of course that will have a penalty on your costs for the initial run, but for a long term that will be much beneficial. So here I have stated that wing wall thickness is zero point 0.4 meters. My T1 is the top slab thickness. My T2 is the inner wall thickness. So you can have the different thicknesses. T3 is the outer wall thickness. T4 is bottom slab thickness. A1 is the haunch dimensions. So the vertical dimension of the haunch. So the software will generate the haunch based on the averaging depth. Okay, it will not model exactly trapezoid here, but instead of that, it will model equivalent thicknesses of rectangle or rectangular plates. Okay, here you can model the soil fill along with the pavement. So in case you have a soil fill, we get to increase the load or gravity load on our box culvert. Along with that, you get a load spread or load dispersion mechanism as well. So for this demonstration of the modeling, I'll not cover those soil fill part, but we'll surely discuss about that in later slides. In transverse direction, so this is the longitudinal direction, or this is the way the channel flows. If I would want the users to be more clear, probably I'll just straight, right? So sorry about it. Okay, so my channel is something like this. So my water flows in this particular direction, and these are the openings that allow the movement of the water flow, and above that you'll have a moving traffic. Okay, so this is the direction of the moving traffic and this is the direction of the water stream. Generally you will have water, but sometimes it might be the case that on the upper level you have a traffic movement in this direction of the box culvert. However, at the bottom floor you can have the traffic movement in the orthogonal direction, in the direction in which stream flows. Okay, so it is very much possible. So in case you have a difference of utilizations, you must always bring in the considerations based on that particular utilizations. In the transverse direction, we'll have carriageway. We have multiple options for providing the static loads or the permanent loads on this model itself. So in the ends, we have the crash barrier loading. This B3 is the crash barrier width. This B4 is the footway width. And then we have a D dimension, which will demarcate your entire carriageway width to the center line. Here we have defined the size of plate elements as 1 meters, and B5 here is assumed, or the clear carriageway width is assumed to be 7.3 meters. Or let's go with 10.9 meters. We have other parameters are okay. Now here comes the input for soil subgrade reactions, right? This is the input we generally get from our geotechnical team. However, if you are an independent engineer, you most of the independent engineers tend to estimate these values via simple calculation of allowable bearing capacities divided by allowable settlements. Those might not be correct in all the cases. Those are estimates, but they are not always right. You might have a very lower stiffness at the center of these box culverts, whereas you might have a higher soil stiffnesses at the ends of these. So, uh, depending on what is your soil subgrade modulus, in this current input, we only have one. So, the single soil spring stiffnesses will be assigned to all the base slab elements, of course. Again, here we are modeling the general type or a linear soil support element. In case you want to go for a compression only soil spring supports, which actually soil is, soil never takes tension, it always goes in compression. So when you are using the general element, or when you are using a link which can take both compression and tension, or a spring which can take both compression and tension, we must first of all ensure that there is no tension involved in your foundation design. Then only you can proceed with the linear assumption of these springs. If in case you can see that there is a tension coming in your model, that means that soil will be able to take tension, which is not the practical case, right? Soil never takes tension. So you must revise your model by changing all those linear springs to compression only, and rerun it for a non-linear, or the load combination turned to a load case. And then you will be able to see the contact loss at the bottom of the foundations or the base slab of the box culvert. Now, length of the elastic link, what do we mean by that? So the bottom slab, let me just save this file. Just a minute. Okay, so length of elastic link basically is your connection between the slab center line and the soil profile. So what I intend to say is, for example, I'll try to demonstrate. Okay. So say this is your base slab thickness. Now base slab thickness will have a lateral force as well, because this is a 3D box element, right? This is a 3D box element, and it can have, of course, forces in this direction. So the slab will also have forces in this direction, right? So what we intend to model is, we have to model this height. If we are modeling the center lines, we are assuming that the forces will be multiplied at this particular level, right? So the soil level starts from this. So any load that is applied at the center of this slab gets multiplied by this height to get an additional moment at this particular level, right? So this particular node should be able to see the force in this direction, and along with the moment due to this lever arm of depth by 2. So we'll use shear springs in these elastic links to have this model effect. Okay. So that is why we will use a length of elastic link of base slab by 2. I hope I used a 0.45. So 0.45 by 2 is 0.225. We'll take the loads as usual. The pavement loads, I'm just keeping the default values. Currently, I'm keeping ASHTO codes here, but I'll use a moving load of Eurocode. Please note that the software will not generate, or the wizard will not generate the moving load as of now. We'll come back to the model later and we'll update the moving loads as well. Okay. Uh, Rest of the values, you have self weight that you need to apply. You have a pavement load. So the pavement density is 23.563, whereas the pavement thickness we did define here as 65 thickness. Of course, the pavement thickness will never be 65, but depending that you have only one pavement layer on the structure, and every time that layer gets damaged, you remove the layer and then only apply, rather than what happens actually on site is they just keep piling up on that same pavement layer again and again, so that pavement thickness gets increased to a very high extent, right? So during the design, if you expect that such will be the case, that your pavement thickness might exceed what you have assumed for, so in that case we must always take those expected thicknesses of the pavement. Say for example, you think that the pavement might not be removed, and they might go for 2 to 3 times the surface coating when the pavement gets damaged, right? So of course after that you'll see a lot of more cracks. So in that case the removal of pavement, it surface coat itself is beneficial. So then the pavement will again be applied to the RCC level, right? But if you expect that they can go for a multiple surface coating on those culverts, so please do account for that additional pavement loading thickness. Okay. So currently I'm using 65 thickness, and I'll go ahead with the, okay. So here are some of the things that I would want to discuss. You can input your soil properties. Here I'm using 35 degrees of soil friction angle, the weight density of the soil to be 20.421. You have live load surcharge of 9.5. You can change this to 10, so it won't matter. Okay. So what this surcharge is that you during the construction or during the service life of the culvert, you will have a lateral load coming in directly from the surcharge or live load surcharge. Okay. Now this surcharge of course can be of two types. You have a dead load surcharge and you'll have a live load surcharge, right? If for example, I'll just take an example that would be better. So they sorry for my sketch. So let's say they constructed, or we constructed a culvert, and then next to that we constructed a soil, or above that we have a pavement, and above that we have a pavement. Okay. And above that of course your traffic runs, right? You'll have a traffic load that will give rise to your soil surface or live load surcharge. So due to this moving load, you accounted for your live load surcharge. But if you constructed a very thick road next to the soil or above the soil next to it, what would happen is that this part of the soil is going to now see a higher surcharge load. Of course some part of this thickness will be replaced by the soil, right? Will be replaced by your pavement. Sorry, probably I should have used different color. Yeah. This is my soil. After that, your pavement gets constructed, right? Your pavement gets constructed here. So what would happen is that your surcharge, dead load surcharge also got increased. Ideally, this will not always be the case. So that is why if you are accounting for live load surcharge, that should be good enough. Okay, so you can have both type of surcharges, your dead load surcharge, your live load surcharge. Of course, your surcharges do have different partial factor or load combination factors depending upon the nature of that surcharge, whether it is arising from variable action or a permanent action. Okay, so here I'll discount any ground level. I'm assuming that there is no water underground pressure or uplift for the purposes of this demonstration. There is a line load from the crash barrier with a self weight of 10 kilonewtons meter, and the crash barrier has a width of defined the values B3 units, which is zero point 0.3 meters. Okay, so zero point 0.3 meters of crash barrier with a self weight of 10 kilonewtons meter. The sidewalk or the footway has a unit weight density of 23. You have a crowd loading, of course. If you have a footway, you might have a crowd load as well on that particular level, which I'm currently assuming to be 5 kilotons per meter square with a thickness of zero point 0.3, or you can go to a lower thickness of zero point 0.2 as well. Now comes the temperature gradient part. I'll probably come to this. I must show you the loading part as well, since we are actually discussing the loading part. Okay. So we discussed something about the loads or the different kinds of load in the model as well. It would be prudent if I just created the geometry. I'm sorry about it. So I just create the geometry. I'm using the weight of this thermal coefficient and I'll hit apply. Okay. So this created my geometry. I'll just go to the structures, project preferences. I'm sorry about the structures type and align top. Okay, so my structure looks something like this. You have a wing wall model, you have a two cell box culvert here. Uh, I use some values, they might not pass or they might pass. We'll look about that when we come to the design part. Okay, so what all we have now in the model, we have the springs defined. So let me just show you the suppose or the point springs defined. We have elastic links and we have different kinds of loads. So let me first discuss the type of loads and what are the different aspects of those loading paths. And then I'll come back again to the model to do the further analysis as well as the design. Okay, just okay. I'll share my screen back. Okay, so actions on box culverts would be of permanent nature, and then you'll have variable action, you have thermal action, you have a hydrostatic action, construction loads, and accidental or seismic loads, right? The permanent action arising from self-weight, your earth pressure. Of course, earth pressure has different components of surcharges as well, some arising from permanent load and some arising from your variable action or the traffic loads. So live load surcharges and dead load surcharges are to be applied differently, right? Then you have a traffic load. We'll look into the different moving load models suggested by the Eurocodes. So we also have a thermal loading on the slab or the top slab of the box culvert. We, in case you have a water table above your base slab level or bottom of the base slab level, then you must also consider your uplift. So not just during the service stage, but during the design life, if there is a possibility of water table rising above the bottom of the slab level, we must all again account for uplift forces. Okay, now there is something called as scar depth as well. So generally in a hydraulic designs, we would consider the base slab to be resting below the scar depth, or we would improve the soil so much so that the scouring is controlled, or the scar depth must not fall below the level of the bottom slab base. Okay, because if you are getting a scour at the base of the box culvert, then your soil will get removed and basically your box culvert will no longer be stable. So we need to control for that scar depth, right? So generally when the depth of these is decided, it is assumed that you take the base slab below the scar depth, or you improve the soil so that the scarring is not critical at that level. Okay, so we also have construction staging loads. We'll discuss on this in today's demonstration. We'll not probably cover through the construction stage loading as well. I hope that in earlier sessions my colleagues covered the construction staging loadings when we discussed about high-rise buildings. Then we have accidental and seismic load cases as well. So now, what are in the static loads? So, of course, we had defined the self weight of the structure. The entire structure is a RCC structure, so you'll have self weight, density of concrete times your thicknesses, or uh, right. Then you have pavement loads. So, pavement load, we define the pavement thickness along with the density. If I could just show you in the model itself, we define the pavement thickness, probably loads, yeah, right. Here we define pavement density along with the thickness of the pavement in this node. This is the pavement thickness. The model values might show you differently, but we have used the earlier values. Okay. So then for the crash barriers, we have inputted a line load value of 10 kilotons per meter. These values are different. Then you have a foot overload or sidewalk loads, which will ask you for the densities along with the thicknesses and the live load of crowd. Okay. So those are the different types of loads that are defined in the model. Okay. There are settlement loads. So generally, if you have a stream width, higher stream width, or even the carriageway width is higher, you might see that soil density, or uh, if you are not compacting the soil enough on site due to site restrictions or due to the cost involvement, then it is very much possible that the stiffness of the soil is different under different support conditions or under different supports, right? When that happens, then you will get differential settlement between these. If your box culvert settles all together, if there's a equal settlement at all the nodes, then that is not a problem, provided you don't change the hydraulic design, of course. You stay within the limits of hydraulic design for this box culvert, then it should not be a problem. Otherwise, if there's a differential settlement, then generally you will have forces arising because of those differential settlements. Okay, so let me just make my point clear, probably, or we'll cover this in the next slides when the time comes. Okay, so now comes the earth pressure. Probably I'll show you in the model what was generated as well. Okay, so for this particular model, we went to box design, we went to box culvert. Okay, so here we use the values. I saved the wizard so that the value is not lost. Okay, so here we use the values of 23.565 for pavement loading. So I'll just try to match those values. I'm sorry, I closed that. Okay. So here you have a dead load, and along with that you have a pressure load applied, right? So the loading can be provided because these are plate elements, and if we have modeled the plate elements, we can assign the pressure loads, right? Define pressure loads is the how you can assign the different families of pressures depending on the utilization or the type of the slab there is, or you can directly assign the pressures. Just define the load combinations here, input the pressure values. Pressure can be applied in the global X, Y, or Z direction, or the local direction of the plate elements. Okay. So here you can see the pressure. The pressure is of 1.5 value. So this is because of the pavement. If you can directly go to check the values, we used a pavement density of 23.5631 times 0.065. That should give you 1.53 kilonewton per meter square of UDL. Okay. Okay, I did this. I should not have removed that part. So I'll go to structures, loadings, then okay. So we checked the pavement thickness basically gives you 1.51 kilonewtons per meter square of UDL. Then, in case you want to apply the line loads on this part, or any of the balustrade loading as a line loading, then you can also go with the beam loads. You can model a dummy beam. If you have modeled the plate and you want to assign the beam load, that's not possible, of course. So we have to model a dummy beam to transfer the loads. Please note that in MIDAS chain, to be able to transfer the load, we must connect the two members via the nodes. If you model a single beam from this node to this node directly without intersecting those nodes in the intermediate meshing nodes, then the force will not be transferred from this beam directly to these walls. Okay. Now here you can see that in these zones we said that we have a higher loading as well. So we said that there's a dead load of this one. So you have a crash barrier load of 10 kilonewtons per meter, and then the crash barrier thickness itself was around, I think, zero point 0.3. We can check that via meshing. So the mesh is generated because of very nodes. I'll just check the zero point 0.3 meters, right? So please feel free to ask any questions if you have in the question box. Okay. So zero point 0.3. So we have assigned 10 kilonewtons per meter divided by zero point 0.3, of course, that would lead you to 10 divided by zero point 0.3 is 33.33 kilonewton per meter square of this loading distributed into a zero point 0.3 meters of span, which will again give you 10 kilonewton per meter of the load, right? So that crash barrier is not a single line load, of course. It is distributed to a zero point 0.3 meters of thickness. Even though it's small, you can model it as a line beam. So same thing. Okay, here it is distributed as a pressure load. Apart from that, we modeled the temperature gradient as well. So I would like to discuss some more on the temperature gradient, but before that, let's check our earth pressures as well. So the software generates the earth pressure for you as well. So let me just activate that part and you'll be able to see the earth pressure, right? So earth pressure is applied equally on both ends. We define the surcharge as well as we define the surcharge values of 9.56 957 kilonewton per meter square, along with the weight density, right? So there's a soil height and then we have a friction angle. So this estimates the pressure coefficient or the earth pressure coefficient in the state of rest. Okay, so for the state of rest, you have a earth pressure coefficient that is denoted by 1 minus sine phi. So coming back to my presentation, probably, sorry about that. Okay. So coming back to my presentation, if you have K naught, which is estimated here by 1 minus sine phi, which is from JK's theory. Okay. So 1 minus sine phi gives you the earth pressure coefficient at rest. Along with that, you have in place, you have applied the live load surcharges, which was around something 9.1, right? So I'll just open up the box, right? Here you have 9.57. So first of all, we'll multiply 9.57 with the factor of 1 minus sine phi, which is 1 minus sine 35, is 0.42 factor multiplied by 9.57 gives you some 4.08 kilonewtons per meter square of lateral load pressure. So on top of this slab, you should be able to see the values based on that. Along with that, we'll also have some other loads. Just a minute. Okay. Then apart from that, you also have pressure coming in from the soil. If you have not modeled any water level, so the pressure goes constantly using a linear line down to the bottom. So the height of the structure multiplied by your K naught into density of the soil would give you the base pressure at the bottom. Okay. So that is how we can arrive at the base pressure at the bottom. Now, if I just show you the entire geometry, so the base pressure or the earth pressure is generated not just for the box culvert walls, but it is also generated for the wing walls as well. Okay, so wing walls will of course have the lateral pressures out of the plane of the wing walls because you have a soil fill in this particular direction. So you'll have soil pressures outside of this. Okay, even though you have a soil on the outside of this some in some cases, but the initial design assumption would estimate the reinforcement in this wing wall, assuming that the soil between these wing walls have to be constrained by these wing wall themselves, even though there's a soil outside in some cases. Okay, so we must design for these wing walls assuming that the soil inside has to be restrained by this wing wall. Okay, so that is how we would generate or we would get the values of earth pressure. Then we have crowd loads, of course. We already determined that crowd loading is 5 kilonewtons per meter. So if you see, this was your footpath, this portion was your footpath, right? This portion of the top slab was your footpath. Then next to it is your, sorry, this is your crash barrier area, and then next to it is your footpath area. Apart from that, this entire region will be your carriageway. Okay, so now here we also had few options. Let me just go back to here. Okay, so as per Eurocode, we have different values of thermal gradients. So as per EC1 of 1 of part 5, the surfacing thickness also governs your thermal gradient. Now thermal gradient is basically a temperature difference between the top of the slab and bottom of the slab. Okay, or you can say top of the wall or one face of the wall and other face of the wall. But in box culvert design, the differential temperature on the wall and the base slab is of no relevance. Why? Because it is in contact with soil always. Okay, in our case, if we had soil on top or soil fill on top of our top slab as well, then we would not be assuming any temperature gradient, at least for the top warming case in this model. We may go for bottom warmer than top for some cases, but still the temperature gradient will be of less relevance if you have a soil fill, a significant soil fill on the top slab of the box culvert. In our current model, because we have not assumed any soil fill, it's just pavement above, we will consider for the thermal gradient. Okay, now in MIDAS civil you have the option to assign the thermal loads via different methods. You have element temperature method. Element temperature method would generally be applied for beam elements. Then there's a temperature gradient method. Then you have a beam section temperature method. So there are different methods using which you can apply the thermal loading on the structure, be it either line element or a plate element. Okay. Now, as I said, EC1 of part 5 gives you two criteria for the thermal loading on the top slab in case you don't have soil fill, significant soil fill on the top slab, right? It states is that during the summers, the top would be warmer than the bottom. So you will have a differential temperature because on the bottom slab, you'll have a shade temperature, right? So top will always be warm. Top will always be warmer than the bottom. Now, it states about the different types of decking. Decking will always matter when we are estimating the thermal temperature because materials differ, even the color of the surface also affects the temperature of the structure. Okay, so if you have a steel deck, you will have a maximum differential of 18 degrees between the top and bottom. That means top is hotter by 18 degrees when compared to the bottom portion of the deck. In composite decks, we have a reduced value of 15 because steel can take or absorb thermal temperatures easily from the outer environment. So during the direct radiations from sunlight, the top portion will get to a higher temperature as compared to the bottom. The composite deck will have RCC on top. So it will reduce the absorption of the heat from direct sunlight. So that is why we see a reduced temperature here. In type 3 concrete deck, we see concrete box girder or concrete slab. Okay. So in our case, the slab is currently of concrete slab. Okay. So ideally the temperature should be 15 because even though you think that the section entirely would be a concrete box girder, concrete box type, right? But the top surface, the distance between the top and the bottom surface is quite high. So we would still consider it as a concrete slab, and I would apply a temperature differential of 15 degrees Celsius between the upper and the lower surface of this concrete structure. Okay. Now, during the winter, the temperature reverses. The bottom portion of the slab becomes hotter, whereas the bottom portion of the slab becomes hotter, of course, when compared to the top portion of the slab. So that is why you will see an opposite differential of temperatures, and that too the value has reduced. So we are assuming that during the heating or during the expansion process you are getting a higher temperature, but during the contraction process we are getting a lesser differential part. Okay, what this would do is this is going to introduce your flexural stresses in your model. Okay, and this will lead to a higher stresses in your slab along or across the cross section of the slab itself. Now, note that there's a note in Eurocode which says that the surface coat or the surfacing thickness decides what is going to be this differential of temperature. Okay, so if these values are as per 50 of depth of surfacing, but if you have a higher thickness or if you have a lower thickness, right? So if you have a lower thickness, of course, you'll have same temperature, you cannot go higher than this. So if you have lower thickness, which would not be the case, so at least you'll have a 50 of surfacing thickness. But if you have a higher thickness than this, then what would happen is your top slab will not be as hot as possible or as in the case of 50 right? So then what the code says is for type 3 you go to the concrete slab, and depending on what is the surface thickness of your case, say for example you move to 100 surface thickness of instead of 50, so you will apply a reduction factor of zero point 0.3 or you'll apply a reduction factor of zero point 0.7 multiplied to 15, right? So zero point 0.7 times 15 would be your 10.5 degrees Celsius of temperature differential instead of 15 degrees of differential temperature. Okay. Whereas the code is not taking any advantage in the bottom portion or the cooling case. Why? Because you have a surface coat on the top surface, which is decided or which is governing in the top warmer than bottom condition. Okay. During the cooling condition you have a bottom slab which governs, so that is why the code is not taking any reduction in that part. Okay. So this is how we'll estimate our temperature loading. So if in this case I could change temperature gradient to 15 degrees Celsius as per this code, right? As per this code, but I have assumed a pavement thickness of 65 mm, so I'll have to adjust or linearly interpolate between 50 and 100 and 1 and zero point 0.7 to estimate the exact temperature value. For the purposes of a demonstration, I am assuming here the temperature gradient of 10 degrees Celsius, and this will assume that this temperature gradient is same for both the expansion as well as the contraction case. If you want to change the temperature case, so let me just show you here. This is the temperature case generated by the software. I just right click now, it will show you the 10 degrees Celsius. Here it says that the top is hotter than the bottom. Let me just increase the size of this. Okay. So here it says that top is higher than the bottom, and in the uh, contraction case, the bottom will be at a higher temperature when compared to top. Okay. So if you want to update the values, you can directly go to the table and just update these values, right? So just let me just see. These are all arranged by the gradient. So sort them. I'll sort them in load case. So I'll just sort them in load case wise, sorting values, right? And I'll directly update the values to say negative 8 degrees Celsius or something, right? So and control C and just select all the 10 values, negative 10 values. Yes. And apply. Okay. Okay. I think, oh, yeah, I included this. So you can just change and apply. Not a problem. Just control V. So the values change. So the differential temperatures will also change for these codes. Okay. So we can change the other temperature in case that is a constraint when generated via the wizard. So that will not be a problem. Okay. Now, one important point to note is that this was a linear assumption. So code has suggested two ways of estimating the thermal gradients, right? First is the linear approach where you directly assume that the top is higher than the bottom or the bottom is higher than the top and linearly interpolate between the two faces, right? But there is also a non-linear approach suggested by the code, okay, where the code has given you the different temperature differences based on the thickness of the concrete slab. So the one that we currently looked at is the concrete slab, which is 3A instead of this concrete box. I'm sorry about this incorrect markup. So 3A concrete slab, 100 surfacing. So these values are dependent on the 100 surfacing. If you want to correct for it, you can come to annexure B table B.3 of Eurocode 1 EC1 of 5 and correct for those temperatures based on the surfacing thickness and depth of the slabs. Okay, so in our case we have 0.45, so somewhere around here our heating and cooling temperatures would lie. But for this demonstration I'm using the linear estimation, but I hope the users understood between the two temperature estimates of the linear approach as well as the non-linear approach, and how they have to correct for the surface thickness. Not just that, if you currently note that these values represent upper bound values for dark color. So this dark color means that the Eurocode has also differentiated between the thermal temperatures owing to the color of the surfaces. So if you have white color of the surfaces, or you'll have a higher reflection, so lesser of the thermal absorption and lesser thermal gradients. Okay, so that is how the code has targeted to adjust for those color of the surfaces. Okay, now we also looked at shrinkage strain and thermal coefficient, right? So this is a shrinkage strain and this is a thermal coefficient, and if you try to estimate the shrinkage strain from the codes using the Eurocode, the calculation of course is a bit involved. So you estimate the total shrinkage via the summation of drying shrinkage and autogenous shrinkage. Drying shrinkage is arising because of the loss of the water once the concrete starts hardening, and autogenous shrinkage is because of the chemical reactions in the concrete itself. So the drying shrinkage majorly depends on the ambient relative humidity. Of course, if your environment outside is drier, then that means it can absorb more water from the concrete. So you'll have a higher drying loss, right? If you have a higher humidity outside, then the concrete will not lose much water during that duration. Your notional size of the member, which is basically a ratio of area and perimeter, that just states that what how much area is available for the loss of water. So from which how much is the surface area to allow for the loss of the water. So that is higher the notional area, higher the shrinkage, right? And the cement class, of course. Uh, then autogenous shrinkage basically depends on the chemical composition. So the combined values tend to be of the order of 200 to 400 microstrain for exposed members, right? If you were to calculate that, you will have to follow the Syria guidelines to calculate the total shrinkage. Now, in current case, if you noticed, I only applied the temperature gradient at the top of the slab. And then we also generated the shrinkage load, which is also applied as a temperature load on top of the slab. So why we applied the shrinkage load as a temperature load? This is not a temperature load, right? Shrinkage load is not a temperature load, but in software, this is applied as a temperature load to bring about the equal deformations. Okay, so that is why we have assigned these shrinkage strains as temperature. Now, how do you arrive at this negative 20 value, right? If you were to calculate the shrinkage temperature based on the shrinkage values, right? So I think I have this right. Okay. So first thing is, why only top of the slab? So drying shrinkage needs drying. Walls and base are cast against soil that we already covered. So slabs, top slab only undergoes your shrinkage temperature, right? Your wall and base slab are always in contact with the soil, so we'll have not much loss of water because there is a relative humidity of 95 to 100%. But in the top slab, because of the relative humidity and other factors, there will be a loss of water apart from the autogenous shrinkage, of course, right? So autogenous shrinkage will happen through in the entire structure, but major component, which is the drying shrinkage, happens only majorly in the top slab part. Okay. Now the second is the casting sequence. Base and wall shrink substantially before the frame is closed. So generally we'll cast the base slab, then we'll erect the walls, and then we'll top it off using the top slab, right? So the top slab cast glass shrinks after closure against mature stiff members. So generally the thermal restraint that is seen by the top slab only. Why? Because your end walls have hardened. Now they can provide sufficient stiffness to your top slab to not allow it to shrink. So that would put your reinforcement into a state of tension. So that is why we must account for shrinkage, right? Now, in MIDAS, we estimated the shrinkage using a temperature. We applied a temperature of 20 degrees Celsius. So we said that the typical values can be around 200 to 400 strain. So I assumed a value of 200 microstrain, which is up this thermal strain of upsila th to be 200 into 10 to the power minus 6 divided by your thermal expansion of concrete, this alpha c. So upsila th divided by alpha c will give you the differential temperature. If you just divide 200 into 10 to the power minus 6 by 10 into 10 to the power minus 6, you will arrive at a temperature of 20 degrees Celsius. So that is how the 20 degrees Celsius is estimated by the wizard. Okay, I hope you understood that point. So apart from all this, I think we have covered all the loads generated by the wizard. We saw the dead load, we saw the pressure load, we saw the gradient temperature in expansion as well as contraction case. Then we saw the earth pressure loads generated, and we have not considered any water table here. And then we saw how the shrinkage is applied in the model, apart from the crowd load, which is your live load part, right? Now let's come to your loading part, how to assign the moving load. Okay, so here, first of all, we added the moving load part directly in this. So we go to static loads. We were working in this criteria, right? Now we move to moving load part. But before that, I would like to describe or discuss what are the moving load models available in Eurocode. Okay, so we have different moving load models in Eurocode. EC1 Part 2. More specifically, we have load model 1, 2, 3, and 4. Okay, so load model 1 contains or consists of tandem system as well as the UDL system. Tandem system is basically the axial loads with the axials with the wheel loads, whereas the UDL systems are the area loads applied to a patch. Okay, now the lane number 1, lane number 2, and lane number 3 means that if you have one lane only, then you will use a tandem value of 300 kilonewtons per axle. So if you have two tires per axle, that means 150 kilonewtons of tire load or wheel load. Okay, uh, as well as you have a UDL load, so you'll also apply a UDL load of 9 kilonewton per meter square. This load is not applied to the entire span, but it is only applied so as to bring about the worst case of the loading. Okay, the load model 1 consists of or includes the dynamic amplification in the characteristic value. So these values do include your dynamic amplification already. Okay, now here for example, you have lane 1, 2, 3. So you can have a carriageway width. Based on the carriageway width, you will estimate your lane width. The lane width, I'll probably come to that, okay, after a few slides. So uh, once you have determined the number of lanes, then comes which lane is the most critical. That will be termed as lane number 1. The second most critical will be lane number 2. So based on this, the sequence is decided, and then you have a remaining area. What all is not coming inside the lanes is the remaining area, and remaining area also gets a UDL load of 2.5 kilotons per meter square in load model 1. Okay, so please note that this is not a single axle value, and that will have be constant for the different lanes. So if you have a one lane of carriageway, then you'll use a 300 kilotons. If you decided or use you found out that you have two lanes, so the first lane or lane number 1 will see 300 kilotons, and the second lane will see a 200 kiloton of axle load or wheel load of 100 kilotons. One axle has two wheels here. Okay, and similarly the UDL loads. Okay, so that is how the load model 1 is decided in Eurocode, now, or defined in the Eurocode. Now load model 2 consists of single axle load. This is majorly required to perform the localized checks. Okay, So this is basically used to perform the localized check on the slab designs. The single axle load has a 400 kilonewton of load, which includes the dynamic amplification factor. Okay, generally used for dynamic effects on shorter spans. The contact surface area of each wheel should be taken into account, and the contact surface area is defined as 0.35 meters by 0.6 meters. In the load model 1 also we have defined the contact area of the tire. Now this contact area is very much important for the determination of load that your slab sees. That has to do something with the load dispersion angle. We'll come to that in later slides. Just wanted to mention that. Okay, then we have load model 3. For box culverts, generally load model 3 and will not be required. Okay, load model 3 basically consists of or comprises of special vehicle load. So where relevant models of special vehicles should be defined and taken into account. So it has to be a choice. If the bridge is significant, then you'll have to assign the special vehicles. For the design considerations, the national annexure may define the load model 3 and its condition of use. So it depends, or the different national annexures may have different SV loadings. Annexure A gives guidance on standard models and their conditions of applications. Depending on these models under considerations, you can change the speed of these vehicle loads. And if you change the speed of these vehicle loads, then you must also account for dynamic amplification factors for these loads. Okay, so at slow speed we need not account for dynamic amplification factor, but at normal speed a dynamic amplification factor should be taken into account. If the structure is to be designed for abnormal load, then vehicles from load model 3 will need to be considered. Load model 4 is crowd loading. If relevant structure should be represented by a load model consisting of UDL of 5 kilonewton per meter. This 5 kilonewton per meter square also includes your dynamic amplification factor. Okay. Now, if you have a loaded length of higher than 10 meters for footway or cycleway bridges, the code also allows you to reduce this UDL. There's also different load models for fatigue loads as well, but those fatigue load models are generally used for specific purpose of fatigue verification. Okay. Now, as per Eurocode and as we saw in load model 1, we need to determine what would be the total number of lanes in your structure. So depending on the carriageway width that we have assigned, so in our case we assigned a carriageway width of 10.9, right? So here in using this formula, if you have a carriageway width of greater than 6 meters, then you use an integer of carriageway width by 3. Now this is a clear carriage width. Okay, this does not account for your footpath or the crash barrier width, or if there is any accidental, sorry, any guardrails inside of or at the medians, right? Protected medians. So we must not include those widths in this. So this is a clear carriageway width. If you're in this particular case, we have a 10.9 clear carriageway width divided by 3. So we should be getting some 3 number of lanes in our case. Okay. Now, whatever in is in access goes to the remaining area. So when we looked at this lanes, right? When we looked at the lane definitions, we saw that we can have a total number of 3 lanes, because 10.9 by 3 is 3.3 3.6 value. So that is saying that to use the integer value, so in our case it is just 3. So we have 3 lanes, and then whatever is remaining goes inside the remaining area. So 10.9 minus 3 into 3 is 1.9 meters of remaining area. Okay, so 1.9 meters will be loaded by 2.5 kilotons per meter, and the rest of the lanes would be loaded as by this tandem as well as the UDL load systems from load model 1. Okay. Now, the load model one spacing is also defined by the code. The spacing between the tires is 1.2 meters, and the sorry, the different spacing between the axles is 1.2 meter, and the spacing between the tires or the wheels is 2 meters, and the spacing between axle is 1.2 meters. I'm sorry, and the contact area is zero point 0.4 by zero point 0.4 meters. Okay. Now, coming back to our model, probably I'll just show you the modeling part. Okay. So I'll here we have an option of I'll come back to the yeah. Let me just switch off this load so on display. Okay. So now we'll define the moving load. Please note that the wizard will not define the moving load. So we'll have to assign the moving load now. So first of all, we have traffic line lanes in civil annex. So you can do if it you have modeled a beam element or the line element, so you'll have to define the wheel loads as a traffic line lanes. So if you want to assign this, currently in this model we don't have lines, but the option looks something like this. You define the lane width, which in general case is 3 meters for Eurocodes. So this is the eccentricity. If you want to change the center line of the vehicle, wheel spacing is 2 meters as per the codes. Then we have transverse lane optimization and vehicular load distribution. So when you make a beam model or the bridge model using line elements, so there is no plate. So for the transverse load, what we do is we make either cross beams or we use lane elements designed for the vehicle loads, right? So it is possible that your load or the wheel load might not always fall on the single straight line where the beam is modeled. So the software allows you to allow the distribution via the cross beams. So in transverse directions, instead of plates would model the beams, cross beams, and using those cross beams you can dump the loads on the primary girders of the bridge. Okay. Not relevant to our case though. I'm just trying to explain you the different philosophies of the load application. Note that the explanations are not specific to a software, but the application procedure is of general nature and can be implemented um, to other softwares as well. But overall, the logic would remain the same. Okay. Now here you must define the track along which the vehicle would move. So, and then you have to define the moving direction, whether it is going to be a forward direction of the vehicle movement, backward direction of the vehicle movement, or both. Generally, we would design for a moving direction of both, and why that matters is because your loading might become critical based on the directions. Okay. You have preceding and succeeding axle loadings, and they are not always symmetric, right? The spacings are not symmetric, the axle loads are not symmetric always. Okay. In such situations, which wheel load is in front and which is in back would determine what is going to be the maximum critical values for your designs. So that is why your moving load direction becomes important in the consideration of moving load analyses and to envelop the most critical design. Okay. So you have traffic lane options. Currently, in our model, we only have plate elements. As you can see from the elements, we only have plate elements, right? So if you have plate elements, we'll go for traffic surface lanes. Here I have predefined some of the lanes earlier. So now this is going to be the crash barrier, right? Your vehicle direction is in this direction. Your vehicle would move in this direction. The vehicle motion is going to be in this direction. This is going to be the soil slope. You have wing walls arresting the movement of the soil in the direction. This is the direction of the stream. You can see the walls here. Probably I'll just show you the extruded view. So this is giving you a better picture of the model. Right now, to align the slabs on top, to align the as you can see, currently the model is center line. So to align the slabs on top, we'll go to project, go to structure type, and just use the align top of the slab. Okay, so now you will be able to see we also modeled the haunches best. As I said, here we'll not get a trapezoid beam or the haunch. Here the haunches are estimated from the average thickness along that length. Okay, now here, as I said, we have the different lanes defined. So I'll go to loads, I'll go to this, I'll go to the traffic lanes. Okay, so in lane direction, what we had is we defined lane width of 3, we have a wheel spacing of 2 meters, and we would define transverse lane optimization. Now, what is transverse lane optimization, right? Transverse lane optimization is that you have defined a vehicle lane of 3 meters. Okay, let me just go back to the presentation a bit. Yeah, here, right? So you have defined a vehicle lane width of 3 meters. Your center to center between the wheels is 2 meters only. So the remaining is 3 meters, right? So 1 meters is in axis. So you are allowed to shift your vehicle in that remaining 1 meter, of course, right? So to shift that, because you don't know what is going to be the critical position of this vehicle when placed along that lane, the vehicle will not always follow the center line of the lane for the movement. It can shift inside its lane, of course, right? So to account for that, MIDAS Civil NX offers you the transverse lane optimization with allowable width. You can define the width of the lane that you want to optimize for, right? Now select the plates that you want to assign to. So basically here you'll have 2-point loads. And just if I just delete it, you select the nodes. Let me just change the values. You select the nodes and okay. So here you select the starting point and the ending point and just apply. So that will define you the lane. So this is lane 1. Now lane 1 is defined at an offset. So I think here I have not defined the offset. So in case you want to model an offset, because your lane will not exactly fall on this line, right? So you can put an offset over here. Okay, offset distance to lane center. So the first lane will not move on the crash barrier part. So here the distance would be, just give me a minute please. So you have a crash barrier of zero point 0.3, then you have a footpath of 1.5, right? And then we have a, just a minute. Okay, then we have a spacing between these curb as well as the axles to be of zero point 0.5, right? And then there's a vehicle uh, wheel width of 1 meters itself, center to center. So the first value would be around 3.3 for this lane, right? So similarly you can enter the offset distance of 3.3. Okay, now moving to the other lane as well. So again, you have defined the two lanes. This is offset of 7 meters. Earlier you had an offset of 2.5 meters defined. I have used some arbitrary values for calculation of 2.5 meters. You can update this value as well. Now the other lane that I have defined is at an offset of 7 meters. Adding the half of the other width as well, okay, from the lane. So if you were to actually calculate, what could I show you probably is, just a minute. Okay, so say this is the your crash barrier, probably this is the width of your crash barrier, then this is your footpath, and then zero point 0.5 is allowed for your first lane, right? Or the axle has to be assigned at a zero point 0.5 meters. Now the center of the lane would be 1 meters from here, right? So from the end, what would be this distance? This is going to be your center line of the first lane. Similarly, for the center of line of the second lane, what is the width of the lane for your second? So this is 3 meters. This is 3 meters, right? So I would add, first of all, this length would be 1.5 meters, and half of that would again be 1.5 meters, right? So lane 1 will be at the center, which would be 1 plus zero point 0.5 plus 1.5 from your footpath, and then zero point 0.3 from your crash barrier will give you this center line lane. Then add to that 3 meters would give you the second lane. Then add to that again 3 meters would give you the third lane, right? Now, after that would be your remaining area. So here you also have the option of defining your lane as well as the remaining area. Okay, so once that is done, once you have defined the lanes, I hope the viewers are clear about how to define the lanes. Now, once you have defined the lanes, we must define the vehicles that will move on those lanes, right? So I'll just, sorry, I'm sorry about this. I have added some standard wheel loads. So that we discussed what is going to be the load model one. So this is a culvert design. We'll follow the load model one loading part. Now, these are what we saw in the codes, and these are some xi factors for tandem system and xi factors for UDL system. This will be changing your load combinations for the different variable actions of persistent, quasi-permanent, and your characteristic. Okay. Here we also have the option to consider contact area. Now, what I mean by contact area, okay. So just a minute. Okay. Okay, so I think we discussed what is cross-lane transverse optimization. I'll just have to discuss the. Okay, so what do you mean by why is that a tire footprint important, right? Or wheel footprint important? Uh, Currently, we have not assumed any earth fill thickness in our model, but the code states that as per EC1 Part 2 of 2003, the wheel loads are to be dispersed along the fill depth at an angle of 45 degrees. Okay. Now, say if you have a pavement thickness of say 65 thickness, right? And you have a slab depth of 450 thick. So the center of the at the center of the slab would be the as we would estimate the pressure loads from these tires. Okay, so say you have 150 kilonewton of a tire load divided by zero point 0.4 times zero point 0.4 is your tire pressure at the top of this pavement, right? Which is 937.5 kilonewton per meter square of patch load in zero point 0.5 meters, zero point 0.4 by zero point 0.4 meters, right? Now, the code states that obviously the slab at center depth will not see this high tire pressure which is applied at the top. The code allows us to distribute this tire pressure to a higher area depending on what is the height between the center line of the slab and the top of the application of the load, so which is the pavement thickness. In current case, it will include the earth fill. I'll come to that in a second. Okay, so the first part is we would account for the pavement thickness and then half of the slab thickness, and we'll distribute the loads at a 45-degree angle. So once your area increases, which would be h by 2 plus pavement thickness, so you'll have a slope of 1:1, right? So you'll have an increase in the area over which this particular point load or the wheel load is being applied. So that would help you reduce the loads as well as the design forces on your plate elements. Okay, this is one part. So the contact area is increasing, so contact pressure will reduce, and this will help us to reduce the reinforcement design in the thickness of the slab. Now this is just one part. Now EC1 part 2 states that this angle to be assumed as 45 degrees angle, right? Now if you were to have a soil in between, generally for box culverts you can have a very high fill height, right? So you can have a 1 to 2 3 meters of fill height as well, right? So if that is the case, then you'll have a very significant higher area. So in PD 6694, the publication has said that we generally do not get such a high dispersion angle because the assumed stiffness of the pavement will not be same as the soil. So they have suggested a lower dispersion angle, which is of 30 degrees to the vertical. Okay, so once now, please note that this is 45 degrees from the vertical as well as the horizontal, but the PD 6694 states that the 30 degrees will be from vertical. So this shape of the cone will be reduced. So the tire footprint area that or the loading area, contact area that the slab center will see would be reduced. Okay, but of course, if you have a huge earth fill between, then still at 30 degrees angle, it will be significantly reduced as compared to what your pavement is getting from the direct tire contact pressure. Okay, so that is what we mean by load dispersion through the fill. We must account for that to help optimize our quantities, reinforcement, and cost in the design of the culverts. Okay, now what if you have two wheels next to each other? Then you'll have a portion of the slab which will have overlap from the two loads, right? So PD 6694 has also stated that wherever you have a overlap in the zones of these pressures, this is the soil fill case. PD 6694, these diagrams relate to the earth fill case. Okay, in our current model we have not assumed earth fill, but I just wanted to cover all the aspects of the culvert design. So we are discussing how the earth fill can help reduce the contact pressure or the area loading that is applied on the slab itself, which can further help us reduce the reinforcement in the design of the culverts. Okay, so if you have overlap, then we are allowed to take the in this common zone. We have to account for the stresses or the pressure arising from the both zones in this particular fashion. So B is the area load coming from this wheel. Say W1 is higher than W2, so width B into higher load divided by the entire load spread of L1 plus A times, which is the overlap of A from this wheel 2 times the wheel 2 divided by the entire spread of L2, okay, which is from wheel 2. So that is how we will combine the forces, and this is only for two tires giving the overlap. If you have multiple tires providing or more than two tires giving the overlap zones, then we can use the local pressure based on the most heavily loaded segment or meter strip as appropriate. Okay, so this is one case. Now the other case would be, what if you are very near to the support? In that case, you are not going to get the entire dispersion angle which is estimated from here. If you are cut short in this particular length, so the spread angle is not achieved to the full width. In that cases, we must use the reduced width of the load spread for the determination of our loadings on the slabs. Okay, so this is what I meant by the contact area. Consider contact area terminology. Okay, so okay, just sorry, the load has been defined, so we'll have to update that. Okay, so I hope the users are now aware of the load dispersion factor. We also have the option of looking at the forces at the concurrent groups. Okay, so for example, you have multiple supports, but you want to know that when I'm having the maximum value at this particular support, then what is the force on the other supports at that particular or the same concurrent reactions, right? So when fz is maximum at this particular node, what is the value of fz for the other nodes as well as the other values, right? So that is the purpose of concurrent groups. Now we have done two things. We have defined our lanes, which is this. Okay, we have defined our lanes. We have defined the lane 1 and then the lane 2. Okay, we could have defined the lane 3, but for the purpose of demonstration, I have only defined lane 2. I, Ideally, we should define 3 lanes, and then we'll also have some part which will go into remaining area portion, which loaded by 2.5 kilometer per meter square as per load model 1. Okay. Now, once that is done, then we can go to results, load combinations, and then directly click on the load combinations auto generation. Okay, so I'll just go to for the concrete design because we want to perform the concrete design as per the codes of selection. So you can select the Eurocode and then perform the load combinations or generate the load combination for the fourth case. In rail traffic, you can have all these live loads in characteristic value or the frequent value, and you can generate the load combination. So these are the different load combinations generated by the software, which has the strength load combinations along with the service load combinations. Okay, so the moving loads are also considered in all these combinations, okay, selectively. So the load factors depend on that as well. Now, please note that the load factors are determined by what are we defining in these types. Instead of the names, the type of the load would define what is going to be the factor in the load combination when auto generation is performed. If auto generation is not performed and you are adding the load combinations manually, then it is immaterial as to which load case you are having it in. Okay, so long as you are not using the auto generation feature. Okay, now once this is done, you can perform the design of it. Now here you also have the option of the analysis of it. You have the option of selectively running the static load case, the influence line, and the moving load case. Please note that once a model is generated for the static loads, first of all, run it for dead load case as at least one vertical load so that you can ensure that your system works. Okay. Once you have established that your structure is intact and is not giving any abnormal deformations in dead load case itself, then you can go for further moving load analysis. Because if you have assigned everything and later on you find an error, it becomes quite difficult to correct for the error. Sometimes in smaller models it is easier, but if you are working with a bigger models, always run the model for one lateral case and one vertical case, at least to ensure that your model is working fine. If it's possible to run the eigenvalue analysis, then do that. It will show you wherever you'll have a disconnectivity in the model. Okay. Okay, so analysis case is done. Okay, so I forgot to also explain you about the links, right? So let me just discuss about supports. So we'll just discuss about the supports that is being used. I'll just open the view. So on the entire boundary. Okay, so these are the supports defined. Probably I'll switch off the lanes now. I'll display, right? Okay. Now let's discuss something about the supports. So in the initial setup, when we were defining, we assigned soil spring stiffnesses, right? So how these soil spring stiffnesses are determined? Let me just shed a light on that as well. So I'll open the wizard that I have saved to be able to see the values. So I assigned 1000 kilo per meter cube. This is quite low, of course. My mistake. I should have used at least 10,000 kilonewton per meter cube. Okay, so let's say that the values run now. Okay, so say these vertical soil springs have been defined with a stiffness, and the stiffness is determined by 1000 kilonewton per meter cube. So I'll directly determine the spacing first of all between the two nodes. Okay, so I see that the distance between the two nodes is 0.91 in one case. I'm sorry about this. Okay, so in x direction it is 0.91, and again in x direction it is 0.91. So the tributary for this particular node would be half of this length and half of this length, which will be 0.91, right? So if I just switch on the loads, sorry about this, I'll cancel this, I'll cancel this. I'll check the boundary. I'll switch on the elastic number, elastic link number, right? Okay. So here you can see the elastic link number is 65. So I'm just trying to match the values of stiffnesses generated by the software. Okay, with manual calculations. I'm assuming that the value of 1000, or in practical it would be around 1000 is quite low, of course. That's my mistake, of course, during the entry of the inputs. But if 1000 kilonewton per meter square is assumed to be true, then we'll check at the spring stiffnesses or elastic links. I'll go to elastic links. The value that we are looking for is the elastic number 65. So I'll look at the elastic link number 65, which has a tributary area of zero point 0.9 meters. So 1000 times 0.91 should give you the values of 910 value. Okay. So I think we use some different values. A minute. 1000. Okay. Okay. In any case, the value should match your assumptions. I think I updated the soil spring stiffness values. So if you have defined the modulus of subgrade reaction as 1000 kilonewtons, so for this particular node, the tributary area would be the distance between these two nodes, right? So of course, this is a quadrilateral, so I just assumed 0.91, but it has in both the directions. So let me just query it. Okay. Yeah, this length as well, right? So zero point 0.3 in that direction and 0.91 in that direction. So it should give you 1000, so 273. So half of this, I'm sorry. Yes, 136. So what I wanted to show you is, just a minute. So if you were to ever match what is the elastic stiffness of this, so half of this tributary area, half of this tributary area, then between the T nodes is half of this tributary area, right? So basically this node is taking its stiffness from this much tributary area. So this entire length is 0.91 meters, and this total length is zero point 0.3 meters. So if we reduce it by half, then it will become 0.15. So 0.15 into 0.91 times 1000 will lead to 136.5 kilotons per meter square. I think we use the same value of 136.5 kiloton per meter of stiffness for this particular node. So I hope you understood now how is this soil spring stiffness for the elastic links has been determined. Please note that not always you have to manually input the soil spring stiffnesses like this. We also have different support uh, springs. So if you had defined the base slabs, you can directly assign the soil springs to those distributed springs on the face of the planar face, along with the compression or linear elements with the modulus of subgrade reaction for these springs. But in that case, it would not have the extra length of depth by 2, obviously, because the springs will be assigned to the center of that plate element, right? So in that case, if you want to account for that extra eccentricity, so the only option would be elastic link, but that is not going to lead to a very higher or significantly higher forces for a structure such as this. So it will be safe enough to ignore for this extra height given by the elastic link of depth by 2. So if you want to use the spring stiffness as supports surface springs, you can use that as well. But please note that there will be a difference in the results, but I do not expect them to be very much high. Okay. Now, we assigned that, okay, the soil stiffness was to be assigned for all these nodes, but we see some of the fixed supports in these particular nodes as well, right? So, for example, this particular nodes are assigned with the springs, the spin supports in x direction, right? Or the spring supports with the very high stiffness in x direction. Okay, x direction is the global x direction. So what this is doing is that this is making your structure stable in x direction, so that the structure will not slide. Why? Because when we define these elastic links, we only define the axial stiffnesses in these elastic links, and they have no resistance to any lateral forces arising from the loading. Okay, because we have assigned the just let me switch on the loads, right? We have assigned the lateral load to this because this is a symmetrical structure and the loading is symmetric as well. So you will net value will be 0. But if you have some difference between the soil levels on the two sides, because ideally the soil will not be equal in all the cases. If you have a sloping highway, then you might see different values of soil height on the two sides, right? And if that is the case, then you must always model the difference of soil pressures on the two sides, and also try to see how much sliding you are getting, because sliding will not be possible on the other side of the wall. You'll have a huge soil uh, quantity or the volume to resist that in passive resistance, right? So exactly sliding will not happen, but if there is any difference in the soil pressures, then we must account for to locally design for these walls, okay, for the local design of these wall elements. Okay, I hope I'm clear on this. So these supports have been defined for the numerical stability of this analysis. Why? Because there were only vertical stiffnesses assigned, nothing to restrain the model to stop sliding in x direction, right? So that is why these have been restrained, and they have to be restrained in a uniform manner such that you don't create any asymmetry in the structure. Otherwise, your structure will rotate about that particular nodes. Okay. Now, what about y direction? So that is why we have defined one support in this direction, right? So this particular node assigns the resistance, infinite resistance in both x and y. So you can see ss and yy, right, at this particular node. So that will make your model numerically stable in y direction movement as well. You do not have any load supplied in this direction. Obviously, if you have traffic movement, then you might see some loading being applied in this direction as well. The load of soil pressures on these wing walls are equally balanced on the two sides. If the heights were different, then soil pressures will also be different. Then whatever would be the difference will, you can see directly that in the reaction of this node. Okay. So that is why that is how the supports of the Calvert model has been defined. I hope you understand now the reason behind the support assumptions or support assignments. Okay, I'll move back to my slides. Probably I'll try to cover. Let's just run the model with the time for the time being, so that I can show you the results. Okay, I'll come back to my slides. Okay, so we discussed about the load dispersion through the field. Then there will be accidental loads. Please note that these are the localized effects, of course, because if you have accidental loads, they must not impact your entire structure design. But locally, if the accidental forces create any asymmetrical loading on your structure, then you must always design for those asymmetries. It will not always be the case that a vehicle hits your crash barrier on two sides equally, right? They can hit either on the left side or on the right side. And when it hits, obviously, you will have some kind of torsion generated in your resisting system. Okay, so your box system should be rigid enough to take that. Obviously, you'll see some base pressure increment on one side, and you'll have some reduction in the base pressures on the other side. But because we have a base slab with a box, then the resistance to these minor lateral loadings would be quite huge. So these cases will not govern. But if you have bridge sections where the decks are very slender, and you cannot discount for these particular loads, so we must account for the accidental loads on crash barriers, lateral loads. Also, sometimes when we model the crash barriers have handrails, right? So this is about the local design, not the global design. So handrails often see the live load, not just vertical live load, but they have to be also designed for lateral live load. So the guardrail will see a out of plane moment arising from the live load, both vertical direction as well as the horizontal direction. Okay, so we must consider that for the design of the guardrail. And then because you have guardrails connected to your crash barriers with base plates, so those forces get transferred to the crash barriers using those base plates in terms of probably torsion. Okay, so those are some local checks that we must not skip, at least when it comes to the final stage of submissions. Structurally, they are generally not governing, and whatever sizes we generally use for our previous submissions or from any of the other standards are good enough to account for those loads. Okay, but that is not to say that we must skip those loads altogether. Now there's also a chance that the vehicle that you designed for, okay, if you have any curbs during the accidental loading cases, it is very much possible though for the vehicle to run over your footway, right? Currently we have not assigned any load on the footway from the vehicles, but it is very much possible that your vehicle runs over the footway part. Now there will be a case that when vehicle runs over the footway part, then you might have less live load on that as well, right? So there's some addition and some subtraction of terms. When you'll have a vehicle running over that footway, then there will be less live load existing on that system. So keep into mind when you account for those loads. But there's a possibility that your vehicle might run over the footway, which has not been designed for that live load arising from the vehicular movement. Okay, because vehicular movement is supposed to be on the carriageway instead of the footway, but in accidental cases you will get that load. Okay, also because we have in this model not considered any uplift, but we must always if the situation or the hydrological or geotechnical report states that you have a water table above the base of the bottom slab during the design life of the structure, then we must always account for the hydrostatic pressures arising from that water table. This will give you a higher load on your walls for wall designs, as well as it will give you a higher uplift forces, which might increase your forces on the base slab design, okay, which might increase your reinforcement in the base slab design on the top face. Also, apart from this, you'll have to perform the uplift check. These are some sort of stability checks that we need to perform in cases of uplift. But in culverts where you have a very high soil fill above the culvert top slab, there this might not govern. But where in our current case where we have not you assumed any soil fill height, right? So there's a chance that when water uplift is present, then the entire structure might lose weight and show uplift. Okay, so that is why we must account for that. Apart from that, there are certain other nuances that we must, as a culvert design engineer, understand that when we use the surcharge for design or the earth pressure for design along with the live load surcharge, right, arising from your vehicular movement. So during the compaction action, during the construction stages, it is possible that when compaction is happening, the load might exceed what you have designed for. So the load might exceed the levels for which you have accounted the live load surcharge. Okay, so you will always have the earth pressure along with that the live load surcharge. What if the compaction plant load rises above the live load surcharge that you have accounted for? So that's a construction stage, but there's a other point as well, that might be a kind of not a long term load, so we can take some reduction in the magnitude of those loads, because the live load surcharges that we have designed for will be of a longer duration when compared to the compaction activity that is happening. So we can of course take a reduction in the compaction magnitudes, but even though after the reduction, if this governs, then you must design for this critical case. So I just wanted to highlight that these are the nuances. One more thing that is important is that during this construction, the concrete might not be hardened before 28 days. And if compaction is carried out before those 28 days, then basically what you are doing is you are applying the design loads on the structure before the structure has achieved its full strength. So the reinforcement that you have provided, assuming that the structure will see such loads when it has gained full strength, will not be enough anymore. Okay, so please make sure that you have accounted for construction loads properly, and always write it in your drawings what is the construction sequence that you are expecting out of the design, or what the design being carried out at the site. Okay, these are the load combinations that we need to generate, the persistent or transient uls, including your live loads from vehicular movement, then your permanent loads combined with your xi factors. Okay, then we have accidental or seismic cases. Currently in this model we have not accounted for, but there are some SLS crack width control checks that we'll see in the design reports being generated by the software. The software is capable of performing the crack width checks for the SLS cases. Now comes the soil structure interaction. Basically, I wanted to discuss in this about the base boundary condition. Generally, we would not assume the in simple modeling part, right? If you were doing a 2D analysis, then you might not assign the soil springs in your case, and you might go ahead with the design assuming the pin fix case, right? So which one is correct? The pin fix base assumption is a modeling convenience, not a soil property. So near real ground can never behave as a rigid pin. Generally, we will assume a spring supported winkler base, and that winkler base redistributes the moments between the base slab and the corner walls very differently to a pinned assumption. Okay, so in case you have pin assumption or fixed assumption, so the moments that you'll see arising from the pin supported case will might be entirely different from what you have assumed for your pin and fixed cases. Okay, and obviously your spring supports are more realistic assumptions, but there's a catch that we would see in next slides. Okay, uh, but obviously the assumptions of pin and fix allows us to do some hand checks. So omitting this step is not altogether suggested, but we should have some sense of how much load is going to arrive based on pin and fix assumptions. And then when we assign the springs, we should compare as to how much was expected. Okay, now, this is the catch I was talking about, that in this current model, we assigned one single soil stiffness value and we expected the entire base slab to be within or to behave with the same soil spring stiffness, right? The first thing that would be is that not all nodes will have the same soil spring stiffness. Not all the nodes, not I misstated that. Not the entire base slab plan will see the same soil spring stiffness. Okay, uh, or the bearing capacity. It would change based on the local or geotechnical reports. It might be the case that you have a different soil or below the drain, and then your footprint of the culvert extends that drain itself. So the soil property changes in those areas. So you are basically looking into different soil spring stiffnesses altogether within a single analysis, right? That's one point. Now, the second point is that whenever we assume that I'll have a soil spring stiffness of, say, 10,000 kilonewton per meter square per meter. Okay, I estimated this, say, using 200 kilotons of bearing capacity divided by 2.5 centimeters of allowable deflection, but which is a very rough estimate and we should not depend on that. But for simple calculations, we generally tend to those values. Okay, so based on that, you arrived at a bearing soil stripping stiffness. Okay, now this is not one single value. Soil, uh, y- the value is arrived by the testing, and testing is not done for the entire area, right? Entire bearing area. So the value might show you a higher estimate as well as a lower estimate. So it is always suggested, when we are carrying out the design, we must use a upper bound and lower bound estimate of the soil springs, so that if soil does not offer you the spring stiffness that you have assumed for, the structure must not fail, right? So the value that you are using for, if you are doing the upper bound and lower bound analysis, that means you have captured for all the critical cases of soil spring stiffnesses and redistributions arising thereby because of this change of the expected soil spring stiffnesses. Okay, so that is the reason we must always perform the upper bound and lower bound estimate for doing the critical analysis or for doing the envelope design, which covers all of the critical cases of, first of all, we are making all the combinations to capture those critical effects. Along with that, the geotechnical parameter arising because of the soil spring changes will also be captured in this upper bound lower bound analysis and is highly suggested by the codes. Now, we also have different earth pressure requirements. In our model, we assume that the earth pressure will always be at rest. Okay, but there is a case that there's always a possibility that wall or the walls of these box culverts move, given that the rigidity of such box culverts are very high, of course. But say your box culvert is a bit slender and you expect some movement in these walls, that means then that one of your faces is going to see the active pressure and the other faces are going to see the passive pressure, right? Now, Whatever be the case, this will lead to difference in earth pressure estimates or the earth pressure loadings that we have estimated. So when we look at PD 6694, it has suggested us multiple cases to account for such variations. So the total, the PD 694 has suggested in total 5 cases. One would be the maximum vertical plus maximum horizontal case. Here, heavy traffic or surcharge is expected while the box is under maximum overburden pressure. This is typically important for maximum overall structural action, right? And the code or the publication document has suggested the earth pressure coefficient itself along with the horizontal traffic surcharge of K naught values for the different load combination or limit states of SLS, equilibrium, and strength. Okay. So what this means is that you must expect for a maximum earth pressure at the base, okay, with the maximum vertical traffic load along with some horizontal value, right? Now, in second case, what they are expecting is that minimum vertical load should be present with maximum horizontal loading. Okay, so these are just some options to account for all the variabilities that the soil, surrounding soil can offer. Okay, then we have a case of vertical traffic in most on-rest position, okay, with minimum horizontal load. So in the other two cases, we saw that we had a maximum horizontal case, and because this is a horizontal value, here the surcharge has also been assumed. In the next case, there is no surcharge assumed, and the earth pressure is also estimated to be minimum, and you have a maximum vertical traffic case, okay. Heavy overburden but relatively lower lateral pressure, important because the vertical and horizontal actions need not reach their maximum simultaneously. Okay. Here, the braking and acceleration load plus maximum vertical load plus active pressure. So far, we have not considered any braking or acceleration load, which will give rise to your horizontal loads along the direction of the track, right? So a vehicle is braking or accelerating above the buried structure, producing a longitudinal action. While the box has a maximum vertical loading, the active pressure combination or active pressure condition is associated with this longitudinal deformation mechanism. Okay, so in such cases, you will see there's a shear deformation can arise because of this braking and acceleration laws, even though the structure is quite rigid in nature. So it might not be significant enough, but still we must know the possibility of it. And PD 6694 does state to check for these cases as well. Okay. Now comes the construction. So we covered some of the nuances arising out of the soil structure interaction. Probably I'll show you the results from the model now. That would be better. Okay. So let's look at the results. We defined the plate load. So the software can generate you the reactions for you. So soil based, not the soil based pressures, the reaction forces. You can see the reaction forces for the different values. I'll just reduce the to 0.5. If you want to see the values in X, Y, Z direction, probably I'll just switch off the values as well. So, okay. So let me just switch on the FX value, right? FX value is quite low. Let me just switch on the values here. Okay, but because we have assigned the pin support, so we are seeing the values in this. We have some reversals as well in the nature of the loading part. So the entire sum of horizontal load in this particular direction can be quite negligible, right? If I go to results table reactions, and if I just check for dead load water and say, okay, in X direction, Y direction, I'm having zero reactions. So net reactions, of course, because you have only applied vertical, so you cannot see any horizontal load. If there is a horizontal load and very minimum, that is coming arising from some numerical issues, convergences. But if you see any significant values arising in X and Y direction, that means that is there is some error in the model. Okay, because we only applied dead load in this direction, and we understand. Now let's see the thermal gradient values. So again, it will be very insignificant. Shrinkage loads, again insignificant. Moving load cases, okay, fx, y, z. Okay, so this is how you can look at the forces. Now let's see the plate forces diagram. So I'll just switch off the values here. Okay, now we'll use average nodal values here. Now I'm assuming that UCS coordinate in x direction and mxx, right? So when I'm seeing the local axis, I'll first of all check what is the local axis generated for all these plates. I would assume that if all the local axes are aligned along this plate elements, then I can look at the values. Otherwise, I'll have to go for a global low UCS values, right? So I just want to check. Okay, as you can see, everything is in this particular direction. So here I'll use the local loads, and this should be same as your global loads because your global axis is aligned with your local axis, right? Now these are the moments in mxx direction. Now for plates, mxx means you're bending in this particular direction. If I just deform the shape, and if I switch off the values, and if sorry, I switch on the entire structure. Okay, so this is the case where you have a maximum moving load. So let me just take the snip of it. So what MXX states is that we determine that this is the X local direction and this is your Y local direction. Okay, and all axes of the plate elements are aligned along this axis. Now this is your X axis basically, and MXX shows you that your bending is happening in this direction. When we'll see MYY, and now here there were two options, element and average nodal. Average nodal just helps you to generate a smooth contours, which will often be the case because if your one element is connected just next to another element, those two elements cannot have different values. They'll have to have some compatibility arising. So that is why we generally tend to use the average nodal values for these element designs. Okay. Now, similarly for MYY directions, which is going to be in this direction, the minor direction of the loads, we should, uh, we are getting these values. And we have defined our lanes in this particular zone. Okay. So this is the MXX and MYY values. Now, here you can also see the, just a minute. Okay. Okay, so we have defined some values. Wood armor moments can be seen in these zones. I'll probably show you the column strip, slab edge moment, and slab middle strip. Okay, so the wood armor moment can be seen. Now, a wood armor moment is generally important. Let me just activate the entire structure. Okay, so generally, if you have a skew shaped structure, so MXX and MYY generally give you the bending moment in the orthogonal directions, right? But when there is a skew in the structure, then you must look into torsion as well. So your plates will undergo torsion. In such cases, wood armor moment is of very important nature. Okay, we must look at the wood armor moment to perform the design of those elements. Currently, in this case, we have orthogonal geometry, so we can go with the design with MXX and MYY moments. Okay. Now here to be able to see the wood armor moment, you have to first of all define the domains and subdomains. So if you go to the domains in this model, I have defined the domain and subdomain already. But let's say I have defined a subdomain, which is a slab top. Similarly, you can define multiple domains, slab tops, bottom slab, the external wall, the internal wall, and separate out the design of these elements. Okay. Now, uh, for example, if you have a slab which the reinforcement direction does not align with your local nodes, local axes or your global axes, then we need to rotate the angles, of course, right? So the subdomain allows you to rotate the angles of the reinforcement in this. So here you have local UCS, and you can change the reference axis, and you can select the vector along which you want to rotate the reinforcement. The V1 will determine the primary direction and V2 will be 90° to that primary direction. Okay. So the assumption is that reinforcement is orthogonally rotated with X and Y direction. Okay, so we have defined the subdomains as well. This is the top slab subdomain in the middle region, edge region, middle region, and column strip center region. Similarly, we can have multiple design strips or the middle strip or subdomains for performing the design of these. Okay, the design will only be performed once you have defined to the software what is the direction of the reinforcement in this model. Okay. Now, the software also offers you to look at the results. I'll just show you the results for influence line diagrams. So the software will generate the influence line diagrams. You have to select the element that you want the line diagram for. Say, for example, I want to generate a line diagram for this particular element. So I just select this one single element and I want to see the force at center of this element. So I'll select and I'll apply MYY, right? Now I'll just see the values and it will show me the values as well. Just a minute. Okay. Now, so this is how we can have a look at the influence line diagram. If you want to have a look at the moving load tracer, which generally shows you what is the most critical position for the element forces selected, right? So for example, if I just select any element, I have these elements. So I've selected this element and I want to see what is going to be the maximum most worst case position of plate force for this. So I can select the element of choice. I'll select the okay, I selected the reaction, so I must see the plate forces and moments, and I'll select the element of choice and I'll select the center element, and I'll say that MXX, I want to see the load position that is maximizing my MXX in this direction, right? So this will give you the direction of the loads, or this will give you the position of the vehicle loads. This is the vehicle loading from your LM1 model from Eurocodes, and this shows you the distribution of the or the location of the different wheel loads. If you want to convert it into a static case which you want to see for your further design, you can just write maximum minimum load file, and this you can directly import it back as a load case into the same file. Okay, so that is how you can have a look at a moving load tracer to see what is going to be the maximum plate force in this location. What would be the most critical wheel position for maximizing your forces MXX in this plate element. Okay, so that is what moving tracer does. For each element you can check that for this particular element what would be your load position that is going to give you a maximum force in this particular element for that mxx myy or shear moment shear. Okay, now we looked at the analysis part. We looked at the forces. We can look at the stresses as well. In plate stresses and plane stresses, we have the value. We can look at the value in top and bottom of the slabs. Okay, top and bottom of the slab, and we also have the sigma effective. But because this is RCC, the one concern for us is XX and YYI along with the wood armor moments. So they are wood armor moments, and stresses will always be aligned along X and Y. Okay, principal stresses you can see, but for concrete, since we design the reinforcement in orthogonal direction, so generally we do not see principal stresses. Okay, if it were a metal structure or a metal beam, then we could have looked at the sigma effective values. Okay, now apart from that, we'll go to the design. Let's say I want to design this culvert for RCC design. So I'll select the code of choice, then we'll have to select some of the parameters. Here you have different Eurocodes for which to design for. You have UK standards, you have recommended version, and then other national annexures for Eurocode. Here you can perform the beam design using singly reinforced beam or doubly reinforced beam. Currently in this model we don't have any beam, so we only have plate elements. Now, for wall design, we can take use of the axial loading plus the biaxial bending, but some codes allow us, or some codes do not want you to take the effect of axial loading on the plate. Okay, for the design of the walls. So, if you don't want to take help from the axial loading in the walls to increase their bending capacity, so you can keep it unchecked. But if you want to take the help from the axial loading of that load column, you can check on this consider axial moment interaction for plate columns, and you can change the strut angle. For concrete generally it is kept as 45 degrees. There are different values you can set, serviceability parameters if you want to design for these elements. So I'll select everything, and I want to check for a crack width of here I can determine or define based on the exposure conditions. I can define from the code, I can define the different stress parameters for stress checks along with the quasi-permanent crack width checks, deflection checks. Okay. Now, apart from this, we have plate models and plated beams and plated columns, because these are not a beam and a column. So to be able to design these plates as beams, we have the option of plate beams and plate columns. Okay. So here you can input the reinforcement minute. Okay, so first of all, you'll have to define the material, which will be for just a minute. For RCC, and I'll change the grade of the steel, and I'll modify to be able to perform the design. Once the reinforcement is defined, then I can go about defining the reinforcement which I want to design for. So here I'll select the subdomain. I have defined the subdomain using node elements domain and define subdomain option. I'll use the average nodal to design for it. Here I can select what is my direction of main reinforcement. I'll open the display options. In design options, in miscellaneous options, I show, sorry, the minute. Yeah, subdomain rebar direction element options. So this should show me the direction of one and direction of two. So for this particular, say this is a top slab edge element. So the direction one is in this direction. Sorry about this. Yeah. So the X direction is the primary direction, which we do want it to be acting as a primary direction, and the other direction would be your distribution reinforcement direction. So the direction one would be your major direction, and direction two would be your minor direction. So here it only asks about the major direction. We define some stirrup numbers. So let's say 5 numbers in per meter, and then the cover at top and bottom. So we have defined the covers. So let's say 10 die of stirrups. Stirrup die has 10, number of 4. So in 1 meter width, you have 4 numbers of this, and then top and bottom cover. Similarly, we have defined for middle strips, and then we can go for the design element. So because we don't have enough time, probably it's better if I show you directly the design report. So the design report for slabs would be printed something like this. I have used a UK and National Lecture for the design. So the design is quite exhaustive in nature. It states the different assumptions of the reinforcement, the load cases that it is designing for, the stress block, the moment capacity calculations as per the code, the shear capacity calculation as per the code, the check of stress limits. I do hope my screen is visible. Please feel free to share any questions in the question box if you have. So the stress limit checks can be performed. The crack width check is also performed as per the code using the quasi-permanent cases. Okay, so this is how you can get the design report from the software. All you have to do is you have to select the structure, you have to perform the plate design. So I'll just select one plate and perform the design of this particular RC beam element. Okay, so that will give you, because I have multiple many load combinations, so it might take some time to generate the word file for all those uh, combinations. So I'll also show you the column report. Okay, so the design for this element is done. So that is what we saw. So detailed design report will be generated. Here you can see the utilization of bending moments. So this is the design report, same as what we saw earlier. Okay, but for this particular case. So the earlier report that I showed, I had saved a sample file, but this is for this particular case. Okay, so that is how you can perform the design of box culvert in MIDAS Civil Annex. So I hope I covered some of the theoretical aspects as well as the practical aspects of the modeling as well as the analysis and design. There's a part of construction staging where that we must also look at. So the soil will not immediately come over the entire box culvert top, that is going to resist in uplift. So in such case where the soil has not been backfilled and uplift increases, so you might see some instability. So we must account carefully for our construction stages. Some of the important things is that we must ensure in our construction drawings that the backfill must be placed symmetrically on the two sides of the box culvert, and if there is a difference, there should be limit as to how much extra can the site compaction go on each side of the box culvert. Okay, it should not be the case that they increase the height to a very up to the top on one side and have only half of the soil backfilled on the other side, because that would lead to unbalanced forces which during design we might not have accounted for. So we must always ensure that our construction documents state the intent of our design. Also at the same point, I like to note that it is not possible for site to always maintain the same height on the two sides. So we should always design for some differential between the soil on the two sides, so that the structure can remain stable during the construction period. Okay, apart from that, if you have precast units, then lifting and handling is also becoming important. If you move the hook quite to the inner side and you lift it, then obviously because the weight is same, you will have a lower moment. uh, okay, but this arm would fail if you move this hook inside, so this arm might go under bending, and this bending might be of a higher value. So it's better to align these lifting hooks as much possible near to the walls, so that the forces can be transferred in compression, in tension to the walls, instead of utilizing the slabs in flexure, because flexure is the weaker mode, of course, right? We also looked at how the MIDAS civil can perform the exposure class checks or stress checks, as well as the cracking checks. This is a haunch detailing, of course. You need to provide the diagonal rebar so as to not have cracking propagated at these reentrant corners. So this is the most desirable detail at the haunch locations in box culvert designs. Okay, so I think I have covered most of what I wanted to. So thank you for the attention, and I'm open to any questions. Can we draft or model in AutoCAD and then import the file? Yes, yes. I think my colleague has already explained in, or I might also have shown you in our earlier sessions, that we can import the DXF file, right? If you want to import a 3D DXF, that's fine. If you want to import a 2D DXF, that is also fine. I already demonstrated in my earlier session how we can import a 3D DXF file and then create the model. I think so. But if not, then we have DXF tracing. We can import the DXF files. Probably I'll show you the format import. So we have import AutoCAD DXF file. This can easily import for the 3D DXF file. So you can make a 3D model or 2D model file and then directly import and then create the geometry. Any other questions? Else, I think I am done with the presentation. Thank you for the attention. Yeah. So I'll stop sharing. Do we have any further questions from the audience? Please feel free to ask any further questions if you have. Hello. I think we'll wait for a few minutes for the closing remarks, and then we can close this session. Over to you, Shristi and other panelists. Thank you. I'll stop sharing now. I have you have my mail ID. In case you have any further questions, you can take the email of Srishti, or you can also mail me for any further technical queries. Yes, yes, of course. You can design hi Ashin, you can design this culvert as a shell element, of course. But shell element design is generally preferred if you have significant out of plane forces, right? And in plane forces. So if you wanted to design the walls, or maybe if I were to design the wing walls, I would prefer to design them using shell elements rather than plate elements or slab elements, right? Because those will have axial forces as well as the bending forces arising out from the soil pressure. But for the top slabs, mostly the loading is in flexure. So we would use the moment design, or we'd use the slab design only. Generally, we use shell design when you expect a significant in-plane forces and you want to account for the shear as well as other modes of forces, right? In slabs, we only account for MXX, MYY, and if you are using wood armor, you are using MXX, MYY, MXY as well. That's a torsional component of the bending moment. So yeah, that's the answer. Thank you for the question. I think the recording might be shared. Any further questions?
Dear sir,
Yes, thank you. Thank you, sir. Over to you. Thank you very much.
thank you very much, Engineer Sumant Kushwaha, for that highly informative
practical and insightful technical session. As a gesture of our sincere gratitude for delivering an excellent and enriching technical session, we would now like to present a token of appreciation to our keynote speaker, Engineer Sumant Kushwaha. This token is presented in appreciation of your valuable contribution to the session titled From Modeling to Design in Eurocodes of Culvert Design, conducted as a part of the SLAICE and MIDAS India CPD webinar series. Sir, please accept this token of appreciation.
Thank you very much for the honor.
Thank you once again, sir, for your valuable contribution. Ladies and gentlemen, as we come to the conclusion of today's program and the successful completion of this 5-day webinar series, it is my privilege to deliver the vote of thanks. On behalf of the Sri Lanka Association of the Institution of Civil Engineers and MIDAS India, I would first like to express our sincere gratitude to today's resource person, Engineer Sumant Kushwaha, for delivering such an informative and insightful technical session from modeling to designing Eurocodes of Culvert design. Thank you, sir, for sharing your valuable knowledge, professional expertise, and practical experience with us. Your clear explanations and guidance have made today's session highly beneficial to the engineers, academics, industry professionals, and students who joined us. Our heartfelt appreciation also goes to MIDAS India for collaborating with SLAICE and for providing the technical expertise, resource persons, and support required to conduct this valuable continuing professional development webinars. We sincerely thank all the resource persons who contributed throughout the 5 sessions and shared their knowledge on structural modeling, analysis, practical design applications, and Eurocode-based engineering workflows. I would also like to extend our sincere appreciation to the office bearers and members of SLAICE, the representatives of MIDAS India, the organizing committee, moderators, technical support team, and everyone who worked behind the scenes to ensure the smooth and successful conduct of this webinar series. A special word of thanks goes to all our participants for joining us from Sri Lanka and abroad. Thank you for your continued presence, active participation, thoughtful questions, and enthusiasm throughout all 5 days of the program. We hope that the knowledge and practical insights gained through this webinar series will be valuable in your academic studies, professional practice, and future engineering projects. Once again, thank you to everyone who contributed towards making today's session and the entire 5-day webinar series a great success. With that, we have come to the end of today's webinar and the successful conclusion of this 5-day continuing professional development webinar series. On behalf of the Sri Lanka Association of the Institution of Civil Engineers and MIDAS India, I extend our heartfelt gratitude to all our distinguished speakers, resource persons, organizing committee members, guests, engineers, academics, students, and participants who contributed towards the success of this program. Over the 5 sessions, participants have been introduced to valuable engineering applications, practical modeling procedures, design principles, and Eurocode-based workflows using the MIDAS software suite. We hope that this webinar series has been informative, practical, and beneficial to your professional and academic development. Thank you to MIDAS India for collaborating with SLAICE and for facilitating this valuable learning opportunity for engineers and students. Most importantly, thank you to all our participants for your enthusiasm, active engagement, and continued presence throughout the 5-day series. Thank you all for joining us. Have a pleasant evening, stay safe, and goodbye.